Welcome everyone. Thank you for joining my talk. So today I am going to talk about how to sandbox a Linux application. If you have any questions, feel free to just write them in the Q&A or find a way to interrupt me. I would like to be interrupted as I go. So the track host will ask the questions you put in the Q&A, and hopefully I'm able to answer them. We'll see. But I'm Martin. I work for Cisco here in Norway, and I'm really sad that I have to say here in Norway, because not being able to join you all in Bristol is really sad for me. I really love being at ACCU. But it doesn't always work, and then I'm really happy I'm actually able to do this talk even though it is remote. The last few years I've spent a lot of time on systems programming and security, and quite some time integrating Chromium into some embedded devices. And I feel like sandboxing ends up being a nice intersection into the world of systems programming and security, which I think is fun. Now, I'm also, as you see next to the last line here, I'm very Linux-based. If you came to this talk hoping that you could use this in a Windows application or take some of this and use it in a Mac application, you're not going to be able to. All of this is Linux specific. And how to do the same thing in Windows or Mac, I have no idea how to do. Only thing I know is that it's very different. And when I'm not banging my head against the keyboard trying to sandbox things and mess around on Linux systems, as you can see here, I kind of like to paint some stuff like these small miniature figures to play D&D. So if you ever bump into me, maybe next ACCU hopefully, and want to talk about Dungeons & Dragons and what I put my players through, then you probably regret it, because I will be hard-pressed to stop. But I really enjoy that. Before we begin, I have an important thing to tell you, and that is to not use any of the code from these slides. What we're going to do today is actually make a sandbox, but we are going to make a really shitty sandbox. You should never run this code. You should never use this code as is. You should actually not write your own sandbox. You should take an open source sandbox or something that someone's actually using and testing and developing, and use that instead of making your own. And if you do not heed this one line, then I take no responsibility. If you take this code and try and use it in an actual production environment, it's going to blow up on you, at some point at least. So please don't. We need to find out what we mean, or what I mean, when I say a sandbox. So what is a sandbox? And I Googled around trying to find some good definition, and I ended up with this one. So what a sandbox is something you use to take an application and run it in a very controlled and restricted environment. And the goal of using a sandbox is not to make shitty code better. The shitty code will still be shitty. It will still be as vulnerable as it always has been. But the goal is to mitigate the impact. Basically, you're using a sandbox to protect the rest of your system, not to protect the application itself. Now, Googling around, I didn't actually find a definition of a sandbox that I liked, so I made up my own, which I'm kind of happy-ish about. You might also wonder, like, why would you sandbox something? Because I'm assuming most of you are developers. You make code. Compared to what I said earlier, you probably make non-shitty code. And you trust your own code. At least most of it. So you shouldn't just sandbox everything. You should figure out what to sandbox. And one of the reasons for sandboxing something is, for instance, that you have an application you do not trust. Which sounds weird. Why would you have an application you do not trust? For me, for instance, I work in an embedded space. And in the embedded world, sometimes you get an application that you for some reason have to run on your device. It could be a closed source binary application that you for some reason need to run to even get anything running on the operating system. And I have not made this application. I cannot inspect this application. But what you could do is to sandbox it to make sure it only does whatever you need it to do. And if it tries to do something else, you have control over it. You might also have an application where you download something from the network, which is code, and then you run it locally. Which sounds like an insane concept, because why would you run something that you just find on the internet? And the thing is, we do this every single day using our web engines, using a browser. I use Google a lot, and this is how a web engine works. As Patricia Oss once said in one of her talks, a web engine is just a big remote code execution engine. It is designed to run code locally that you don't trust, so they're heavily sandboxed. You might also have an application. Again, maybe you can't control it at all. And this has some expectation of what environment it's running in. It might assume a file exists at a certain place on your file system, but on your system, it doesn't. Maybe you're not even able to put a file at that location. It might be as simple as a binary that assumes that /lib contains 32-bit libraries, but on your system, it contains 64, or vice versa. You kind of want to leave that application alone, but you could use the same techniques that you use to make a sandbox to give it another view of the world. And that is basically what, for instance, Docker does. And the fourth reason to actually look at sandboxing is because they are a lot of fun. Now, this is not a good reason to actually make them, or maybe make them for educational purposes. They're fun to learn about. This is not a good reason to make a sandbox and run it in production. It's actually a really bad reason for that, but it's a very good reason to learn about them. Now, on Linux, you have a couple of tools that you use to make sandboxes. You have namespaces, you have seccomp, you have cgroups. You have some others as well. For instance, SLinux is really cool. We'll focus on the three first today. And I view these as like the building blocks to make a proper sandbox. You could use them together with other tools like SLinux or AppArmor or something. They won't interfere with each other, and it's basically just another layer of security on them. But we'll start by talking about namespaces, but before we get to that, let's look at our application. Because there are many ways of actually making a sandbox. This is the first one. And you start by basically having some code that sets up a sandbox. And when the sandbox is set up, you exec whatever your second argument is, which is then the application. So this would look, I don't actually have it running, but it would look something like this. /arg1 /arg2, and this exec thing would basically have this binary sandbox, set up a sandbox, and then run this application with whatever arguments you gave it. And that works. You can do this for every single binary. You can do it for your own stuff. You can do it for binary blobs that you have no control over. But the problem with this is that you need to be a bit more open. You need to mount you need access to more of the files. Particularly, you need access to libraries that this application, this argv1, actually depend on. So you need to mount some libraries, and you could do that. It might or might not be a problem for you. But another tactic is to do this instead. Basically, you build the sandbox itself inside of the application. So you set up the sandbox, and then you just run some application code. There's no executing of another application. Of course, a major downside of this is that this will not work if you only have a binary file, a binary blob that you cannot change. Because you can't just add this setup sandbox code to it without doing a lot of tricks. It's a black box. It's not something you can add stuff to. So instead, to get like the best of both worlds, we do something really nasty. And we use something called LD preload. This is what it looks like, and I'll first show you how it actually works. So we can run our application. I have an application here, run result bin application, which prints out some stuff. All these numbers here are the running processes on the system. Shows me what network interfaces I have, and shows you that I, for instance, have Docker running. I have 0 capabilities. I have a lot of stuff mounted in my root folder, and I'm running as user ID 1000, group ID 100, and I have a PID. This is the process ID. Now, if I want to run this sandboxed, I could do this LD preload result lib sandbox. I made a SO file with my sandbox result bin application. And I really messed this up. Sorry. Next build. So currently, nothing has changed. We're printing a lot of the same stuff. But this is printed by the SO file before anything else. So I'm basically injecting some code into the application that's running before the application. And the way that happens is doing this. So this LD preload allows me to take a SO file with some public symbols, which then overrides the public symbols of later SO files that we load. So in this case, the really nasty stuff is I overload libc start main __ libc start main. I'm assuming, given that this is ACCU, that most of you are C and C++ programmers, and you know that this __ thing is not something I should touch, ever. But I do. This name might change, which will break my sandbox completely. The thing is, with a sandbox, you are, regardless, very dependent on what, especially libc version, you're running against. When we get to seccomp, you'll actually see why. But it's a glibc upgrade might break your sandbox completely. So it's not that dangerous, I hope, to depend on this. And it's what you do. Because you need something that runs before the application that you override, which has to be inside of libc. And the thing we do is we take the main that the application wants to have run, just the main of the application, and we store it into some variable. Then we find the actual libc start main, and we run the actual libc start main with my main function. So I override what main function libc start main is supposed to run. I still need libc start main to do its work, because this is the linker. It'll do some stuff. I don't know what, but it'll do some stuff. So when I get here, this is when libc start main thinks it's called main, but it's calling my override of main. And between these two lines, I'll set up my sandbox, and then I run the actual main. That is how I injected the basically printing of running sandboxed. And to start building up our sandbox, we'll start by looking at namespaces. Namespaces is a way to wrap a global system resource. It has nothing to do with these namespaces. It's a Linux thing to wrap a global system resource, such as networking, mount points, PIDs, you have 8 different ones. When you boot up a Linux box, everything starts up in a namespace of each type. So you start up in 8 different namespaces, one of each type. You can create new namespaces by either calling the clone syscall or unshare. We're going to use unshare. Clone is like a really fancy way of doing fork. Fork is actually implemented using clone. And also pthread create is implemented using clone. So clone is very versatile and does a lot of stuff, or you could do a lot of stuff with it, but it's very complicated. So we're going to skip it and just go for unshare. I'm only going to look into a few namespaces here. If you are making a proper sandbox, you should consider all of them. You might not need all of them, but you should at least consider all of them. And the first namespace we'll look at is the user namespace. Now, the user namespace is a way of isolate the users in group IDs. Basically, you can use it to get a different range of user IDs and group IDs. And you enter it by using clone new user. Now, the permission model is slightly complicated and involves other namespaces and stuff. Michael Karisk just held a talk yesterday on NDC security. It's a 2-part talk. If you want to know how the actual permission model works, go look at his talk. I don't have time to go through that whole thing, unfortunately. What happens is that you can create a user namespace, and it will look like your application is root. It's not really root. And so we're in a Linux world at this point where root is not root anymore. Root looks like it has all the permissions, but the permission check is also checked in the parent namespace and the other namespaces you're in. It's slightly complicated, but root is not root anymore. And this namespace is hierarchical. So you have this namespace here, which is the initial namespace, the initial user namespace. You can create a new one, and then you have 2 files to write to. You have the UID map and GID map file. If you write 01001 into one of these files, it means that you're mapping the ID 0 inside of the namespace to ID 1000 outside of it. And you do that for a single ID. Now you can increase the range like we do on the left side here. Here we say that ID 100 inside of the namespace is ID 688 outside of it. and we do this for 500 IDs. So in the NS2's case, this user will be something that looks like root, while in this namespace, if my math is not completely off, these are the IDs we'll end up with. And you can make more user namespaces. You can have a very deep list of this, or deep tree of this. Yeah. Now these two files is something we need to write to at some point, but to create a new user namespace and enter it, you do this. You say unshare clone new user. So after this line here, even though your UID was 1000 and you had the actual username, you are now running as nobody. You have no permissions. You're basically nobody, so the system doesn't trust you. So what we need to do is make this mapping. And the way to do that is that before you enter the namespace, you fetch the current user and group ID if you want to make the 0,001 mapping. Then you write to procself UID map. Now procself is a magic directory that is the proc directory for this process. And in there you write 0, 1001, assuming this UID is 1000, which it is on my system. And then you write 0, whatever your group is, 1 to procself GID map. And these mappings should give you a running user with UID 0 and group ID 0. Except it won't. Like I said, this is a horrible sandbox. I'm not checking any error codes. And this last write will fail. I'm not allowed to write to this file as it stands now. Because on Linux, you have the ability to change who you're running at. You can add more groups to your running application, especially if you have permissions for that. And you have to turn that capability off. So before doing this write to GID map, you have to first write the string deny to procself setgroups. This allows you to add supplementary groups to your current running user. And if you don't have that, you're not allowed to write this GID map. So let's have a look at how that works. So we do git rebase continue, which I hope is the correct one now. The application hasn't changed at all at this point. I'm not going to run it again because I'm lazy. You just have to trust me. All the same information is here, except I am now running as UID 0 and group ID 0. I'm running as root. As you can see, I also have every capability. This is Linux notation for I have every capability. Equal nothing means I have no capabilities. But I have now every single capability. It looks like. It's not completely true, but it's almost true. Now, there was a reason why we started with the user namespace. The user namespace is the only namespace that you don't need the capability capsysadmin to enter. And by going into a new user namespace, you can create new namespaces that this user namespace owns. So using the user namespace, we open ourselves up to creating new namespaces without actually running as the true root. So an unprivileged process can now create new namespaces. And by the way, one thing I forgot is that, we'll go back to this, on Docker, which I assume a lot of you know about, this default mapping, because Docker uses this to create its own user namespace, and the default mapping Docker uses is 0, 0, and then some huge number, like 4 million or something. I think it's a 32-bit integers. And it's that means that root inside of a Docker container by default is running as a true root, which is something you should be aware of. It has proper all capabilities, not just this restricted one that we're making. Next thing we can do is now we can use a mount namespace. So we'll use a mount namespace to rewrite the file system. We want to create our own root file system that is separate from whatever the rest of the systems is, where we can basically play around, and if something gets more access inside of that corner of the world that no one else has access to, that's fine. To create a mount namespace, you use this clone UNS flag, which you might think sounds weird. Where does new NS come from? And it comes from new namespace. Because the mount namespace was the first one created, way before anyone thought about stuff like containers. And as we all know, when you create something, you don't think it's gonna like explode. It's not gonna be a lot of new things of the same type of thing. So the initial developers thought that, yeah, this is going to be the only namespace ever created, and so we call it new NS. When you create and join a new network mount namespace, you take the list of mount points that you have from the previous namespace that you're from and copy it to the new namespace. They will now be the exact same. You have some capabilities to, for instance, share the view between the previous namespace or just follow the previous namespace without being allowed to change it yourself. But in our case, we kind of want our changes to be invisible for the rest of the system. And we want changes from the rest of the system to be invisible to us. Previously, this was how it worked. When you entered a new mount namespace, you didn't share anything. Your view of the file system was your view of the file system. No one knew what that was. Systemd came in and changed that default. So now the default for most systems is that you share. And you don't really know necessarily what init system you're using and what the default on that system is. So you should start by just unsharing. Make sure it's private. To create and enter the namespace, you just add the clone UNS flag, and that creates it. And after this, the file system hasn't changed. It looks exactly the same. And the first thing we need to do is this. Basically, we're saying that from the root, we set every mount point to private, and we do that recursively. So after this call has finished, you have a private mount namespace. Now you can mess around. Now you can play around and have fun. And we will. What we'll do now is we are going to create a new slash for ourselves. And we do that by first mounting a new temporary file system on top of /temp. By doing that, this new temporary file system only exists for your mount namespace. No one else can see this. The reason for using /temp to do this is, one, there's probably nothing in /temp I need to carry over to my new root file system. And I'm pretty sure that /temp will exist. So after doing this, you can start mounting stuff over. So basically, I create a temp lib64 because I want a /lib64 inside of my sandbox. And what I do is I bind mount this lib64 to my new root file system, basically saying that this place, temp lib64, should point to the same thing as /lib64 points to. And you can do that for both files and directories. And you can then mount up whatever you need for your file system. After you've done that, you can change what your / is. Now you could use good old chroot. That would do the job. The problem with using chroot is that it imposes a restriction, and that restriction is that you can no longer enter a new user namespace. Generally, you don't want to make it too obvious for an attacker that they're in a sandbox, because then they'll look for sandbox escapes. So you kind of want to give them the opportunity. And also, maybe your application needs a new user namespace. They should have the opportunity to use that. So there is a syscall called pivotroot that you can use for this. And pivotroot takes 2 arguments. The first one is what is going to be your new /. Basically, this mount point is going to be /. And then the second argument is where to put the old /. In this case, I made a directory and I told it to put the old / in temp old root. Then you have to cd to your now new root, because if not, you're still wherever you were and you could basically traverse the old root file system. And after this, you can unmount the old root, because you don't want the old / to linger around. So you unmount it and you remove it, and you should be good. Now this is going to change a couple of things. So do the same thing, ld preload, and you see I, for fun, mounted up /sys and /run. My application don't need these directories. You also see that I'm crashing because I don't have a /proc. I haven't mounted a /proc yet because I can't. Because in my PID namespace, I've already mounted a /proc. And you can't have 2 mounts of the same /proc. I'm not sure why. But anyway, you would still then be mounting the old /proc, which would contain every single application running, and that would be kind of useless. So instead, we'll fix that with a PID namespace. Now these are a bit different. You create it by using clone new PID. But if you use the unshare syscall, then you're not moved into it. The kernel developers found out that if they changed the PID of an application on the fly, that kernel change would require user space changes. Because, for instance, glibc and every single libc implementation I've looked at caches the PID. So they found out that it was easier to just not move you into it, and instead said the first process, the first child process of the creating process will be PID1 in a new namespace. And basically what you do, what the view of this is that the kernel will start counting again, counting PIDs. So your first process will be PID1, your second process will most likely be PID2, and so on. And PID1 on Linux is very special, because PID1 is the init process. And contrary to the name, initializing other processes is not the most important work of PID1. Because PID1 is also the parent of every orphan child. Or orphan child process, not actually orphan children, but orphan child processes. They get PID1 as the parent because PID1 is then supposed to do something about them, most of the time killing them, which is not something that's nice to say out loud, but that's what they do. They kill orphan child processes. What you want to do with this is you want to isolate a process from the other processes on the system. And there is a mapping. So there's a mapping from whatever PID you have inside of the namespace to whatever the parent namespace sees. So this NS0 here, this is the initial namespace, and it has an init process, which has some children, 3451 for instance. But that process is in a namespace. So it sees itself as PID1. But the init process here and any other process that's in this namespace will see it as 3451. And you can have hierarchies here. So PID1 in NS3 will be, for instance, 2 in NS2, but then 1024 in the initial namespace. Of course, the parent can see what it thinks it is inside of its namespace, but you can't go the other way. Now, creating the PID namespace is just as simple as creating every other namespace. You just add clone new PID, and now it's created. It's also empty. So to put the process into this namespace, you have to fork or use the clone syscall. That would put the child already in it. You can fork. And then if you're the child, you can do the swap routing thing and then running the actual main and then exiting with whatever result code you got from main. And then as the parent, you would then basically wait for the child process to exit and return the status code. If you don't do this wait, you will send a signal to kill the child process, which is not what you actually want. Now, after doing this, after making a new PID namespace, the child is allowed to mount a new proc file system, which is what we do here. Which I'll use to show that we're now alone, as far as we can say. Let's have a look at that. So, load the lib sandbox with the application. And as you see now, we didn't crash for once. We're running as PID1. I mounted the /proc. And we are the only running process, which is what we wanted. So this process now thinks it's the only running process on the system. It has no way of figuring out if that's actually true or not, but given its view, it looks like it is. The last namespace we'll look into is the network namespace. And the network namespace creates a new networking stack. It gets its own set of devices. It also gets its own IP tables set up. Like it's a full new networking stack. When you create and enter it, first off, you'll use clone new net. And when you enter it, you have one network device, which is the loopback device, meaning localhost, and it is down. Entering it is very restrictive. You can move network interfaces into and out of namespaces. A physical device can only exist, or any device basically, can only exist in a single namespace at a time. If you move a physical device like ETH0 to a new namespace, and that namespace is destroyed, then the physical ETH0 is moved back to the initial namespace. So also if you move it 2 jumps, so you move it from here to here, down here, and you kill this namespace but none of the others, it'll still move to the initial namespace. It's very uncommon to move the physical devices. What you normally do is you use these virtual Ethernet devices, virtual Ethernet pairs. You put one end of the pair into another namespace, you have one in the initial namespace, and then you use IP tables or a bridge device to give this device a route out to the internet. Also, these loopback devices are different. So if you have something in your initial network namespace listening to localhost, an application in a network namespace cannot see that port. It cannot connect to that port because that only exists in this namespace and not in this. So to create and enter one, you just add clone in new net. In this case, I do it in the child. The reason for doing it in the child is, for instance, in the parent, you could then create or set up a network for this child, given that you have the permissions for it. And then you could signal the child that, hey, your network is ready, and then they can go in and run the actual application. I'm actually not going to do that because IP tables is a talk in itself. It is a complicated beast. I barely know it, and I'm not gonna just touch it. I've done more than enough just banging my fingers on the keyboard to try and get something like this up before. But you can do it using IP tables, breached network interfaces, virtual network interfaces. It's a whole thing. But I can show you how it looks when I've removed myself from the network. Next build, and then we run the LD preload. And you see at this point, I've gone from having like loads of network devices to only a single loopback device. It is actually going to be down, so not active. I can easily set it up again. But I have no other network devices, so someone would have to put a network device into this namespace to even start getting any kind of network. Like I said, there are 8 at this point in time namespaces. These are the other ones. If you're making a proper sandbox instead of this horrible one I'm making, then you should use, or at least consider using, all of them, because they protect different things. But let's skip ahead. Let's say we're now done with the namespaces. We set up a sandbox that uses a lot of namespaces. What can we do more? Well, we can use seccomp. And seccomp is filtering of system calls. And when you enable seccomp, you allow system calls exit, sigreturn, read, and write. Which of course is very useless. Because your application probably uses way more than that. So this is the old seccomp. This is the first initial version of seccomp. But today, we have seccomp BPF. So when someone says seccomp, they probably mean this. Now, seccomp uses the Berkeley packet filtering. Berkeley packet filtering is an in-kernel programming language. It's running on a VM. It has a lot of stuff around it, like a JIT compiler and stuff. It's used for a lot of things. For instance, it was created to do packet filtering, hence the name. In seccomp, it is used to handle system calls. So you can look at system calls and you can decide if you want to allow or deny them, or log them, or do something else. You can inspect the arguments to the system calls to decide if they are approved. You can do a lot of things with the system calls. When you use seccomp, you need to consider the target architecture. The seccomp program needs to check the target architecture, not because the binary code is different. But on Linux, the system calls differ depending on your architecture. So x86 system calls are different, or system call numbers are different from, for instance, ARM system call numbers. You might think that maybe x86 and x86-64 has kind of the same-ish numbers, but they don't. They're completely different. And that's why you need to actually check that you're running on the expected architecture, because your actual program will differ depending on if it's running on another architecture. Now, using seccomp, you're actually working on a struct, which looks like this. It has a system call number. It has unsigned 32-bit integer that represents the architecture. You actually have an instruction pointer. So you could use this to say, I allow this system call only in this region of code. I've never seen it used. I haven't tried using it. I think it's really cool, but I don't really have any real world knowledge of how it could be used properly. And you also have pointers to the arguments. Now, this next part is going to be really ugly, because the kernel gives you some tools to make these seccomp filters. And the way to do it is you create one of these sock filter things, which contains lots of BPF statements. You put that sock filter to a sock fprog, and you send that to sysseccomp. And in this case, I set it to set mode filter. You have other modes as well. You could, for instance, just log. I'll get quickly back to that. But the most interesting part of this is this sock filter. This is just an array of these BPF statements or BPF jumps. And what we do here is we say we return. This is a BPF statement where we return seccomp.allow. So we're saying any system call that comes in will allow it. So this is basically whatever you have without seccomp at this point. But we'll put some meat on the bone for this. And we'll start by checking architecture. Like I said, this is important. So you now start with the BPF statement where you load something, a word, with absolute offset into a register. And the offset you use is the architecture field in the seccomp data. This is how you load stuff from this struct. Then, when this is in the register, you have a jump. And you say, I jump if equal to whatever is in the register is equal to arch x86-64. If it is equal, I jump 0. Basically, I just go to the next statement, which is our seccomp.allow. And if not, I jump 1, jumping over to seccomp.kill, which will kill your program. And this checks the architecture-ish. There's actually missing stuff here because x32 would also accept this, and we have to, for x86-64 and x32, check if the x32 syscall bit is set, because x86-64 and x32 have different system call numbers. I'm not actually going to do that. It's easy enough to find, but you shouldn't do this thing anyway. I'll show you how you should do it afterwards. But this is like what the kernel gives you. This is what any second filter you make will boil down to. All of these very, very nice macros. So, if I want to actually check system call numbers, after doing the argument check, you load a new load from this second data, but this time you get the system call number. And then you check if that is, or jump if that is equal to sysexecve. If it's equal to sysexecve, I jump 0, go to ret allow. And if it's not, I jump over ret allow again, and I go to second ret kill. And at this point, you also see there's a change here. I have to update this jump because I need to hit second ret kill with this jump. Because if it's not the correct architecture, I should just kill the program. So I have to jump over these two new instructions. And you continue doing this. Of course, you only have to load this syscall number once. And then you keep going. And you add more and more system calls. And this is the full one for the application I made. And it is very small compared to what you would normally have. Now, at some point, you might upgrade glibc. Or you might do something new inside of your application and you need to handle that. You end up basically using a new system call. That new system call needs to be in this list. And you could decide that, okay, I'll put this new system call at the end. If you do that, every jump above it needs to be updated. Because it needs to jump over this new instruction. Also, you might then want to make your life a bit easier by putting it at the top, because then you only have to change this jump. But then you're forcing one extra check for every system call. So if this new system call is one you do once, and then the rest of the time you're basically spending all of your time doing receive message, you add an extra check for every receive message call you do. So your ordering here matters. For performance reasons, you want the system calls you use often at the top, and the ones you very seldom use at the bottom. And I don't know about you guys, but I am going to mess this up. One of my colleagues are going to mess this up. This is not easy to maintain. And to make it slightly harder, we'll put in checking of arguments as well. Now, if I want to check the argument to exit group, which is what gives back the exit code to the calling process, instead of jumping 22 and allowing exit group, and I have to swap them. I have to jump 0 and do my argument check. And if it isn't exit group, I have to jump over the argument checking things. And to do the argument checking itself, I load into that famous register of ours, in this case, the first argument. And then I check if the argument is equal to 0. If it is equal to 0, I jump to what I hope is allow, and if not, I think I jump to deny. Of course, this might be more complicated. And this check is kind of dumb. Basically, you're saying I only allow exit group if the exit of the program is successful. If not, I'll kill it again. But this is how you can check any argument. But I do not want to maintain this. So luckily, someone made a library for us that does a lot of this for us, basically does all of this for us. With libseccomp, you create a seccomp filter with a default action. The default action in this case is seccomp act kill. Basically, kill the program if no other rules applies. You load it into the kernel, and after this program is loaded into the kernel, I can release my user space handle to it, because then it's just memory. This looks similar to the first raw seccomp usage we did. It looks very similar to the one where we just said allow everything. But this one does more. This one also does the architecture check for you. It checks your target architecture and default uses that, and will add the correct, in this case, architecture check. Which is nice, because then I don't have to mess that one up. Now, to add a new rule to do something other than killing the program, you say seccomp rule add. I want this rule to end up with an allow, and I allow it if the system call number is execve. Seccomp sys execve. And I have 0 argument checks. We'll come back to actually using this one. Now you also see up here, set seccomp arch. This is how you set an architecture if it's for some reason different than your target architecture. It very seldom is. But this scmp sys will take care of finding the correct system call given the architecture you're making it for. So that's pretty nice. Makes it a lot easier to work with. So this is the same list of system call in a slightly different order compared to what we had earlier. Well, it's not actually this. Yeah, it might be the same. Not really sure. I basically wrapped the seccomp rule add into allows libseccomp because I never care about architecture of the arguments in this case. But here I say I can like rearrange and add new stuff without having to worry about jumps. And I can make sure that the most frequently used system calls are at the top very easily. It's really repetitive. It's not fun to make this. It's very, very repetitive, but it's a lot nicer to work with and maintain than the raw seccomp. It's also very, very easy to check arguments. So this 0 meant I don't care about arguments at all. This 1 means I have 1 check for arguments. And that check is, I check argument 0, the first argument to this function, if that is equal to 0. I can have many of these argument checks. I can have multiple for the same argument, so I can check if it's in a range, for instance, or in a set of numbers. It's very flexible, and this is actually possible to work with. So if you're in the position where you actually make a sandbox, I would definitely recommend you use libseccomp instead of the kernel macros, which is going to be very hard to work with. But when doing this, while having fun with seccomp, one question came up for me. how can I compare strings? Because these seccomp check things only seems to work with numbers. They don't care about strings. And I see no way of dereferencing a string. And the reason for that is that you can't dereference a string because the string is not copied to the kernel at the point where seccomp runs. So you shouldn't. Now, if you really want to make sure that your strings are correct, you could have a static variable, hopefully it's constant, put into memory, and use your seccomp to compare memory location with that string. So, for instance, if that string was foo, and you want to only allow some syscall with the first argument of the string foo, then you could do that by having a static string foo and compare the memory location of that foo with what memory location you get into seccomp. Of course, that means that if someone else tries to do that system call with a foo that is somewhere else in memory, then their system call will be denied, even though it's a valid call-ish, like conceptually. But that's how it works. So let's have a look at using seccomp. Let's do this and do build. Now, I do the same thing, and this is really boring because nothing happens, and that's the whole point. Running the program as it should run shouldn't really affect seccomp, or seccomp shouldn't affect a well-behaving program. So instead, let's go and just modify it. So here we have some rules. Let's remove capget. I'm no longer allowed to do the capget syscall, hopefully. Like I learned from Michael Karrisk yesterday, doing live demos, all you should say is, watch this. So watch this. Whew. You see, like everything goes fine until I try to fetch the capabilities, then I die and exit code is 159. To just prove that my shell isn't lying to you, echo 159. Now the question is, how do I figure out what system call that was? If you have an audit log on your system, you can check the audit log. I just use dmask here and I see that, okay, I have an audit log. I see my user ID and group ID. Actually, these are the ones from the initial namespace, not the one inside of the namespace. Same with the PID. I see the full path to the application. I'm using next, so it gets a very funky path. I get called with signal 31. This is the architecture I'm running on. And this is the system call. syscall 125, which is on this x86-64 machine, is getcap. There are some tools on Linux I've never used myself to actually find the syscall name from the syscall number. Because you could take this number directly, put it into your seccomp filter and run it, and it would work. It would work really well, actually. So let's try this. 125 getcap. Wait, yeah. Capget is of course name. So I just do 125. Spill. And then I run it and watch this. Yes, it works as as expected. Now you shouldn't do that because this number is specific to x86-64, x86, x32, ARM will have different system calls. So what I usually do is I find the table of system calls and I just go through it and find number 125, put that into the program. Of course, this is very boring to do, like one-on-one system call. So you could tell libseccomp that instead of killing your program when it fails, you go in and you log it. You allow it and you log it instead, any violation. And then you basically just get a long list of system calls and you can do one-on-one of them. Now, the last thing we're going to talk about is cgroups. And this has nothing to do with cgroup, any programming language. It's more like this. Cgroups, or control groups as the official name is a way of limiting capabilities of groups of processes and also their access to resources. The API for it is a pseudo file system. Basically, you use file system APIs to go in and configure the kernel to do what you want it to do. Now, it all started with cgroups version 1. It was first implemented in kernel 2.6.24, which is many, many years ago now. There's a lot of controllers in version 1. And between every one of these controllers, there was no synchronization of the development. Cgroups version 1 is a mess. It is hard to work with. The APIs are different. It's not pleasant at all. So we'll ignore version 1 because version 2 is available everywhere-ish. Especially-ish, and except if you're an embedded developer like me, you don't have access to it. But version 2 is way nicer, so let's do that. This is the second take of doing cgroups. And just a few years after they started cgroup version 1, someone started cgroups version 2 because they saw that this was going to be a mess. And they needed to fix it, and the only way to fix it was to start again. And they've done a lot better. They just have one big unified hierarchy. The APIs looks more similar. Not all the controllers are available in version 2, especially not in the way they were in version 1, but most are. Now you have a lot of controllers. These, we're not going to go through all of them. We will look at memory usage, CPU usage. Yeah. But you can do a lot of stuff. You can limit block device access. You can you can prioritize network packets. These blue ones at the bottom are not available in cgroups version 2 the same way they were in version 1. In version 2, they are solved using, BPF, or actually eBPF, because all the cool kernel developers these days are messing around with eBPF, because that's cool. You have a structure in cgroups. Cgroups are, the way you see them, they're just folders. I'm actually going to power through this a bit and rather show you how it looks. Now, you have two files for enabling and disabling a single controller. Now you have cgroup controllers, which you can look at to see what controllers are available in this cgroup. If you want to change what controllers are available in a cgroup, you have to modify subtree control in the parent cgroup, which will then change whatever's in cgroup controllers for the current cgroup. Let's have a look at how this actually works. And we'll start by this. Now, cgroups is in, normally at least, sysfs cgroup. This is a big folder. I'll just limit it a bit and make a new folder, ACCU. Now, as you saw, I just made a folder using the mkdir command. And if I go into that folder, I have a lot of files. Because this is not a file system, this is a pseudo file system. This is basically a view into the kernel or into some kernel data structures. So I can make a new one, aptly named X. And of course, X has very little, because I haven't really enabled any controllers in this. So if I, in my parent folder, look at cgroups subtree control, I have nothing. But I can still add processes to it. So if I get the PID of this shell, I can do 5885 into x cgroup.procs. And I can inspect that, cat x cgroup.procs, and I see that this PID is now inside of this cgroup. I can try and delete this cgroup, and I'm not allowed. I can try and rmdir this cgroup, and I'm not allowed, because there is a process in it. So if I kill that process, I can try and, well, let's try and rm-fr anyway, because this is very brutal, right? rm-rf as root should basically be allowed to kill everything, and it's not. But if I then do rmdir x, it is gone. I don't have a X folder anymore. It is completely gone. I destroyed that cgroup. The cgroup needs to be empty to be allowed to delete it. So let's make one again. And let's add a controller. Let's start with the memory controller. So to enable the memory controller, you write the string plus memory to the parent's subtree control. And if I now look into X, I have some new files. And I can take this and move that one into this cgroup. So cgroup procs shows you what processes exist in this cgroup. Now, let's look at the memory controller. And you see I have a lot of files there. Memory max will be a hard limit on how much memory this cgroup can use. So if I look at memory max, it's max. I can use everything. I also have the same type of files for swap, and that's also max. Now, just for this demo, I'll do 0 swap max, because I don't want to do swap memory, because that would mess everything up. Now, what I want to do is I want to allocate a lot of memory. And I have this memory grabber thing, which I will give some numbers. And it allocates a lot of memory, in total 1.1-ish gig. Now, if I don't want it to use that much memory, let's do it again and see, because you can also use cgroups to inspect stuff. You can see that, okay, this is the current memory it's using. And if I kill it, that memory has gone down. So if I give it access to very little memory, like this, actually let's give it a bit more, memory max, and I run it again, I get killed. When I'm getting more memory than whatever I put in max, I get killed, which is what I want. So this is how you can limit memory. You can also limit CPU stuff. Let's just put this back and enable the CPU controller. Now, I can also disable the memory controller because I'm not going to use it anymore. So to do that, you just add minus. And you see, I only have the CPU controller and the memory files are gone. So I can look into a few of these files. Let's start with cpu.max. cpu.max will give you a certain number of shares per period. So max says it will give you everything. If I say 100,000, 100,000, CPU.max, it means I now allow 100 shares or 100,000 shares per 100,000 period, basically one CPU core. So this is one period is one CPU core. If I only change one of them, the first number is what's changing. So I have this thing called a CPU burn, where I'll burn 2 threads and just burn CPU, and they're close to 100%. Now I can limit these. Currently, they're probably running on 2 different cores, so let's go back to limiting them to 100% of one core. And you see they're going down to 50% of their CPU usage. This is basically just burning CPU, and every second-ish, they check how much CPU time they've gotten. And you can limit this a lot. So I can give them a tenth of a CPU. That's not going to be very fun to watch, so let's give them half a CPU. And they go down to like 25% of the CPU time, and if you heard my fan, it would have gone down quite a lot. And I can get them back to max, and they'll start burning a lot of CPU again. You also have something else here. You have something called, which is kind of nice, CPU.weight. That is going to weigh the CPU shares for this C group. So if I look at CPU.weight, it has 100. Currently, that doesn't mean anything. If I make a new subdirectory or a new sub-C group and see what's in that, I see that's also 100. Now, the difference between max and weight is that weight only kicks in if there's congestion, if there's too much tasks compared to the CPU. So if there's no load, it'll get everything. So if I start this again, well, let's first move this one into cgroups.box. So now this left is in the Y C group and the right one is in the X C group. And I can start CPU and burn on both of them. Let's just use a bit. And you see at this point, they're competing for the CPU. You get approximately 50%-ish, I guess. But let's change the weighting, because the weighting is done that you have two, that you take the sum of the child C groups, and you divide the current C group's weight with the total shares they have. So if I increase this right one's C group to 1,000, this will be given 10 times as much runtime, or 10 times-ish as much runtime as the left one. And you see the right one is picking up and the left one has basically stalled. And I can do this further. I can basically kill the left one by just adding weights to the right one. And this left one will now spend a lot of time doing its work because they're competing for the CPU time. And I've said that the right one is always going to win with a big number. The left one will still get its time share, but not too much. And this will be used, for instance, to make sure that one process is not going to be overrun by another process. Now let's go back to having them the same. And let us add something called CPU set into my C group. CPU set allows me to pin certain processes to certain cores. Let's kill this again. I only need one of them now, so I'll use the right one. I now have this CPU set, CPUs. It tells me nothing at this point, meaning I have access to every part of the CPU. So if I pull this back to 2, I have access to the full CPU if I want to. But I can limit that. Sorry. I can limit that to only be running on a single core of the CPU. And you see, currently both of these threads are running on the same core and they share it equally. If I want to give it more again, I can give it 1 and 2. Now, if I make a new C group, a new child C group of this X C group, and enable CPU set for that C group, I can go into that C group and say, I want core 2 and 3 for this child. Now, this sounds weird. Basically, I'm allowing the child C group to get access to more of the cores than I had, or cores that I don't have access to. And it turns out it doesn't, because you have this CPU's effective, which tells me that effectively I only have access to core 2 because I'm not allowed to use core 3 because my parent C group tells me no. Okay. So let's kill these ones, stop burning my CPU. Well, we actually went through C groups, but you also look into stuff like SLNX and AppArmor if you're making a sandbox. the tools we've gone through now are basically available on every single Linux system. SE Linux might not be, but if it is available, you should use it.